Hello AP Chemistry and welcome to Chapter 16, Acids and Bases, where we take the basics that we've been talking about since Chapter 4, or since last year really, and we just add on layers, right? We layer in a Lewis structure stuff, we layer in equilibrium stuff, we layer in some of the solubility stuff. All of it sort of comes together in this one beautiful, magical chapter, which does require, like it says in that outline, right, that you actually know all those other topics. So please, 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 I urge you, as we encounter something and you realize, ooh, maybe I didn't get it as well as I thought I did the first time, drop by or go review. Just make sure that you do know it, right, so that way you can master this material. All right, because this also does make up a significant chunk of what you will see on your AP exam, right? So this is stuff to know well. All right, so first, obviously, let's talk about some basic definitions. Simple definitions, I guess, would be better. Arrhenius, right? So when we're talking about acids, right, we are talking about things, right, that increase, right, the H plus in solution. And for bases, we are talking about things that increase the hydroxide ion in solution, right? Problem here, right, is that we have to be in solution, which not all reactions are in solution. And then, right, mostly this pertains to strong acids and strong bases, right? In that our things that do this, increase the H plus, are mostly going to be our strong acids, which dissociate to form H plus, right? Or our strong bases, which dissociate to form hydroxide ions, right? So in terms of limitations, one, we've got the whole aqueous thing, and two, it mostly limits itself most naturally to strong species, right? Where in our Bronsted-Lowry definitions, right, we have the concept of a proton donor, right, and we have a proton acceptor. Right, so again, we are still talking about reactions happening in aqueous solutions, right, with water as our background, right? None of this can happen without water in the background. But for our H plus donors, obviously, whatever it is, right, has to have a hydrogen, right, that is able to be lost, right, during the course of this reaction, right? And in order to be an H plus acceptor, what it's going to have is, ding, 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 right, has to have a lone pair. If it doesn't have a lone pair, it cannot function as a Bronsted-Lowry base, right? So do be mindful about that as we're looking at our structures, which is why it's important that we can sort of envision the types of Lewis structures that happen based on location on the periodic table, right? These are all things that, if we can do them, make everything else happen so much more easily. All right, so Bronsted-Lowry reactions. So the thing about this, right, is that they happen in pairs, right? So just like when we talked about redox, there always had to be a reduction accompanied by an oxidation, right? Something had to lose electrons and then something else had to pick up those electrons, and it had to happen together. Same thing here with Bronsted-Lowry, right? In that we have to have something that functions as an acid, in that it has a proton to donate. We have to have something that functions as a base that has lone pairs that can take the proton, right? And then, right, we end up with whatever's left, right? And then that new protonated thing, right? Likewise, down here, we have something that has an H to donate. We have some lone pairs that can take that H, right? And then we end up with that chloride, and we end up with that protonated form, right? Going back to the stuff in your guys' book, right, now we can label these, right? In that if this is something that is an acid, right, then over here, this deprotonated version is its conjugate base, yes? Whereas for water, right, if it's functioning as a base here, this protonated version is its conjugate acid, right? Conjugate pairs. And note that it's always the conjugate of the thing it came from, yes? As in, like, chloride is the conjugate base to its protonated form, yes? Likewise, if we look down here, right, again, chloride is the protonated, the deprotonated version of our acid, right? So this is our conjugate base to our acid, right? And then if we look here, right, this is the protonated form, so this is the conjugate acid to our base, yes? Proton donor, proton acceptor. All right, and then if we look over here, this is asking us to write the formula of the conjugate acid to each of the following, right? And if we think about what it means to be the conjugate acid, what does that mean? Right, the conjugate acid is simply the protonated form of it. Yes, protonated form. And protons are H pluses. So if I add an H plus to that, I'm going to get H2SO3, and my charge is going to change to neutral, right? If I have an F and I add it, or an F minus and I add an H to it, neutral, right? HPO4, 2 minus, because I added an H change the charge by +1, right? If I have to do that and add an H there, now if I have HCO, now it's going to be plus because I've added a proton to something that was neutral. Yes? All right. When lithium oxide is dissolved in water, the solution turns basic from the reaction of this, right? So obviously our solubility rules tell us that will dissolve, right? And then we have our O2 minus plus water is going to give us what, right? Well, we got to look at our options, right? So O doesn't have a proton, right? So it cannot donate a proton, not an option. So it must take a proton, right? Which means we're going to end up with OH minus, right? And if we take a proton from water, we get OH minus. Correct. All right. Which means that if this, we'll just link it, doesn't matter which hydroxide you link it to, right? So if this is going to be our proton acceptor, right, then this is going to be our base, right? And if this is going to be our proton donor, then this is going to be our acid. Yes, does that make sense? And if these are the ones that are going to be linked, right, then this is going to be my conjugate acid, right? And then likewise, this, right, would be the conjugate base of this. Yes, does that make sense? All right. Last up, nope, almost last. Understanding conjugate pairs. So we're going to talk more about this diagram later, maybe not this exact diagram, but the concept later, right? In that, if something is a strong acid, remember you've memorized these, right? If something is a strong acid, right, what's important to note, right, is that it has negligible basicity. Its conjugate base has negligible basicity, right? And if we think about just like dissecting the language here, right, negligible means, right, zero, none, not really something that contributes, right? So negligible means no basicity, meaning that chloride ion has no tendency to act as a base, where base means no tendency to accept protons, right? That's what we were saying. Okay, so no tendency to accept protons, that's what negligible basicity means, right? Whereas down here, these things that have negligible acidity, right, means that they have no tendency to donate protons, yes? Right? No tendency to donate protons, despite having protons, yes? All right, and then if we think about what that means, right, that goes back to what we already talked about when we talked about K values a little bit, right? So we understand that this strong acid, right, dissociates completely, right, or in this case, we're going to write the reaction with water, right? So we're going to end up with this, right, and this, right? Now, if we understand that HCl ionizes 100%, right, meaning that when we talk about what species are in solution, we'd say that there are 0 HCl molecules because they all dissociated, right? That means that this has a K value approaching infinity. Yes, does that make sense, right? If it all dissociates, right, and K is essentially products over reactants, right, there's no reactant. This is approaching infinity, right? Meaning this reaction only has a tendency to go forward and does not have a tendency to go backward, meaning chloride has no tendency to abstract a proton from H3O plus and go backwards. Negligible basicity, okay? Now, if we go down here, this, right, like your book talks about and like we've talked about before, right, we would be better served writing those double-headed arrows, right, and then this would be H3O plus CH3COO minus, okay, which has a K value of approximately 10 to the negative 5, right, meaning that it does not tend to go forward significantly, yes? It does not tend to go forward significantly, right? Which means there's still enough of this left over that when we write a net ionic, we actually go ahead and write it stuck together because that is still the dominant species in solution. Yes, does that make sense? All right, so let's go ahead and tie together that statement from your book. So it says that equilibrium favors the transfer of a proton from the stronger acid to the stronger base, right, to form the weaker acid and the weaker base, right? So let's go ahead and as an exercise, let's go ahead and label all these species, right? So HCl is clearly our acid, right, which means that in this respect, water is our base, right? Which means that if we're linking our species, these, right, this is our conjugate base, right, and this is the conjugate acid to the water, right? Does that make sense, right? And so we're going to transfer the proton from the stronger acid to the stronger base to form the weaker acid and the weaker base, right? So the stronger acid, so if we look at my two acid options, right, this is an acid and this is an acid, right? Which of these is the stronger acid? Right. The HCl is my stronger acid, right? And if we look at my bases, right, between H2O and Cl minus, right, my stronger base is going to be my H2O. Yes, does that make sense, right? As in the stronger acid will give up the proton, the stronger base will accept the proton, right? Which means that these over here are our weaker species, yes? Okay, so for starters, analyzing the second one, let's go ahead and label all of our species, right? So here we have our acid, and here we have our base, and here we have our conjugate base, and here we have our conjugate acid, right? So we have the acid form, which is protonated, and then the base form, which is deprotonated, right? And here we have the base form, and then we protonate it, and that's our conjugate acid. So again, equilibrium favors the transfer of a proton from the stronger acid to the stronger base, right? Stronger acid will donate, the stronger base will accept, leaving us with a weaker acid and a weaker base, right? So if we have a K is equal to 10 to the negative 5, right, that means there is more reactant versus product, yes? That's what that means, right? So then if we look at what our reaction says in this case, right, what that's saying is that this is the stronger acid, yes? In that of my two acids, right, the H3O plus is the stronger acid. It is the one that preferentially donates a proton, right, which is what leaves us on the reactant side, right? Which means that in the land of bases, which is the stronger base, between comparing my options of water or acetate ion, right? Acetate ion is my stronger base in that it is the one that does the accepting of the proton, which leads us over here. Yes? Make sense? All right. Then finally, right, that takes us to one last practice, right, where it says predict whether the equilibrium lies to the left or to the right. So here, let's just label our species, right? So we see what happens to this is it ends up deprotonated, right? So it ends up donating a proton, which means that this is acting as our acid, and this is clearly its conjugate base because it's the deprotonated form, right? Here, which means that this must be a base, and this must be its conjugate acid or its protonated form, right? So then the stronger acid, right, is going to be the one that donates the proton. We have two acids to consider. We have this acid and we have this acid. So which of these ends up donating the proton, right? Let's go back to our diagram and compare water versus H2PO4 minus, right? So there's no assumption that you've memorized this, right? But water versus H2PO4 minus, here's water and H2PO4 minus, right? H2PO4 minus is the stronger acid, right? If H2PO4 minus is the stronger acid, right, that means equilibrium lies in that direction, yes? Because that's going to be the species that does the donating of the proton, yes? Does that make sense? All right. If we look at the second equation, right, again, analysis, right? So we have this species and then we have that species. So what happens to it is that it donates a proton, right? So here we have an acid and here we have its conjugate base and here we have a base and here we have its conjugate acid. So again, so we're just going to start by identifying the acids. So we have ammonium and we have water. So we'll go back to that diagram and we'll compare water and ammonium. So we have water and ammonium, wherever ammonium is. All right, so between water and ammonium is the stronger acid, right? So this is my stronger acid, which means that equilibrium lies in that direction. Yes, does that make sense? All right, thank you for listening. Lots more to come. Be good. Bye.